Hello, everyone. I'm going to get started so we can stay on track. We have a full session, full slate of talks today at RocqPL. So thank you to coming to this inaugural session or edition of RocqPL. It's my pleasure to start things off with a bang. Our keynote speaker today is Ariel. So Ariel Kellison is a senior research engineer at CodeMetal, where she works on ensuring the correctness of LLM-generated code using methods from programming languages, formal methods, and numerical analysis. She received her PhD in computer science from Cornell University in December 2024, and subsequently held a postdoctoral appointment at Sandia National Labs. From 2020 to 2024, Ariel was a Department of Energy Computational Science Graduate Fellow, and in 2025, she was named a Frederick H. Howes Scholar in Computational Science and an MIT EECS Rising Star. And today, she's going to be talking about some of this work on future-proofing numerical accuracy with formal specifications. Thank you, Ariel.
I think my mic is on, yes. I'm really delighted to be here today, and this talk is about some of the work that I did during my PhD on writing formal specifications in Roc with accuracy guarantees, specifically for numerical linear algebra programs, and how I think the Roc community can help with future-proofing numerical accuracy guarantees by writing formal specs in Roc, specifically in the domain of numerical linear algebra. So to start off with, informal specs have played a very important role in numerical linear algebra, and particularly in its success over the last 75 years. And numerical linear algebra has been incredibly successful, so it works astonishingly well. And kind of the canonical, or one canonical example of that, is solving large systems of linear equations. So in this setting, we have like a coefficient matrix A. And we're also given this constant vector b, and we're tasked with finding a solution vector of variables x. And this is like a very important problem in science and engineering. So for instance, it's used in public health models for modeling disease transfer. It's also used in weather forecasting and supercomputing benchmarks. So for supercomputing benchmarks, people solve these giant linear systems of equations to try and rank supercomputers and by how performant they are. So how well do they solve, how quickly do they solve these really big systems of equations. And kind of the remarkable or astonishing thing, I think, is that I can solve pretty much like a dense linear system of equations where the dimension of the matrix is like 10,000 on my machine that I'm presenting on today in around a minute, which is really kind of incredible, especially considering that 75 years ago, a 12 by 12 linear system of equations was given to the mathematical division at the National Physics Lab in the UK, and it was considered an incredibly challenging problem. And you might think like, okay, incredibly challenging for whom? You learned Gaussian elimination in middle school, like why is this hard? Well, it was incredibly challenging for some very influential people. So James Wilkinson was tasked with working on this problem, and he won the Turing Award in 1970, partially for his work on it. And he was working with Turing on this problem at the mathematical division in the National Physics Lab in the UK. And in his Turing Award speech, he says, Turing was not particularly enthusiastic about solving this 12 by 12 system of linear equations, which you might think is simple these days, particularly because he was convinced that it would be a failure. So this leads us to a very natural question of, well, why does numerical linear algebra work so well between especially like solving these 12 by 12 systems of equations being challenging 75 years ago to being incredibly practical on our machines today? Okay, well, clearly the intuitive answer off the top of your head is going to be that advances in hardware have delivered like incredible performance over the last 75 years, right? So as a kind of proxy for hardware performance in general, here I have a plot of the top 500 supercomputers, the top 500 machines in the world, and how they, their like arithmetic intensity. So here, actually, this is a plot of flops per second, so floating point operations per second. This is 35 years ago in 1990 is where it starts, and 2030 is where it ends. And you can see that we go from 1 gigaflop, so 10 to the 9 floating point operations, per second all the way to an exaflop, which we were able to hit in 2025 on our top machine. So an exaflop is 1 billion floating point operations per second, or a quintillion floating point operations per second. So like clearly advances in hardware have had an impact on the success of numerical linear algebra. That's a really intuitive answer that's sort of obvious in some ways to most people. There's another answer, okay? Advances in algorithms have kept pace with the hardware. So for example, we moved from vector processing machines to hierarchical memory, and numerical linear algebra had to sort of refactor many of the common algorithms. Like here I have a simple matrix multiply, you know, a triple nested loop, and we had to refactor this to work on these hierarchical memory machines. And in particular, we wanted to increase arithmetic intensity by, in this example, blocking matrices to reduce the amount of data that we moved. Okay, second intuitive answer, right? Advances in algorithms, clearly, computer science. But there's a third answer that isn't maybe intuitive to most people, but is really well known in the numerical analysis community, which is the Basic Linear Algebra Subprograms, or BLAS. I'm going to continue to say that. Standard provides a stable interface. So in particular, we have these clients. So at the beginning of the talk, I said linear algebra is used across science, in engineering and science. So we have these clients, which are applications, scientists, and library developers, common like NumPy, PyTorch, for example. So at the top of this stack, on top of the BLAS interface, we have these clients in science and engineering, and then the BLAS interface provides for them an abstraction where we have over these very basic linear algebra kernels, like a dot product, a matrix multiply, matrix vector multiply. And really what this does is it provides an abstraction that clients can rely on. And then below, providers, mostly hardware vendors, so providers of these basic linear algebra subprograms libraries, they can aggressively optimize while clients can rely on the stable BLAS abstraction. And yeah, mostly the providers are hardware vendors. So like Intel has its one API that has like a BLAS implementation in it that's highly optimized for their hardware. NVIDIA has CU BLAS or cuBLAS, which is highly optimized for their hardware. But then there are some academic offerings of these libraries as well. So OpenBLAS and BLIS. But for the most part, the providers of BLAS implementations are the hardware vendors themselves. All right, and you might think, well, why would I actually need to use something like BLAS? Why would I actually want to rely on someone else to optimize what might seem to use something simple like a dot product or a matrix multiply? And the answer is that, well, we have these naive implementations. Again, here this is flops on the vertical axis and an optimization technique on the horizontal axis. And if you can see that in the naive case, right, we don't really have great performance. You can add in these optimization techniques that might be simple to think of, like SIMD blocking, like we saw the matrix multiply earlier, threads. But then here's OpenBLAS. That's one of these publicly available providers of basic linear algebra subprogram interface. And we get very, very good optimization in comparison to these simple techniques that you or I might implement naturally. All right. So what does the BLAS standard define? Well, it was introduced in 2001, and it's really a synthesis or a composition of many previous attempts to provide specifications of the basic linear algebra operations. So in the late 1970s, they came out with this level 1 BLAS spec, which describes specifications of scalar and vector operations. For example, I have this scaled dot product on the screen. And then in the late 80s, they came out with a level 2 BLAS, which is matrix vector operations spec. And in 1990, again, kind of addressing the rise of hierarchical memory, they came out with a level 3 BLAS, which is matrix multiply operations or matrix operations. And then the BLAS technical forum standard is the composition of all of these things. It provides a high-level spec for all of these types of operations. So level 1, level 2, and level 3 BLAS. And it really was a meeting of a lot of people working on numerical linear algebra and also in the application space to try and decide what is the best high-level specification for application users for these types of operations. All right, so more specifically, the BLAS standard provides a fixed interface, so naming conventions and arguments, and I'm realizing this is a little bit small on the screen here, but this is an example just like of a summary of the BLAS 3, so matrix-matrix operations. And so the BLAS standard provides a fixed interface, a naming convention, so this is GEM, general matrix-matrix multiply. This is the example that I have at the top of the screen here. So really what it does is it like scales the matrix multiply, and then you add on a scaled matrix to that. And it also provides a family of precision and type variants. So you might want to be able to do this matrix multiply in single precision, double precision. You might want to have matrices with complex numbers, for example. And so it has also options for single complex and double complex. And then it also specifies the mathematical intent, which I think is an extremely important thing here. But it really has like for each operation, it'll have just a basic equation. And I have the basic equation for GEM that is specified by the BLAS here. All right, but there's a little bit of a gap here. So computed results don't always align with mathematical intent, right? So this is like our mathematical representation of that scaled matrix multiply, right? This is mathematically what we would compute in infinite precision given that equation. But here I have this like C hat. Okay, so every element of that matrix C, when we're actually computing this on a computer, is represented in finite precision using a floating point representation. So this is a floating point representation. We have a sign bit, exponent bits, and a fraction bit. So that's every component of our matrix is going to be represented in this way. And there are many different formats that we might use each element would take. So we're probably most familiar with the IEEE double, which has 11 bits of exponent, 52 bits of fraction. Sometimes we use IEEE single, 8 bits of exponent, 23 bits of fraction. And then now, mostly this is used as a storage format, but it's becoming increasingly used actually for the computations themselves, is half precision, so FP16, where we have only 5 bits of exponent and 10 bits of fraction. Okay, so we have these decreasing precisions. All right. And really, what numerical analysts are concerned with in some instances is computing the error, so the difference between our ideal or infinite precision result and the computed result that's represented in floating point. All right, what does the BLAS standard say about what the error should be? So like, what is an acceptable difference between the ideal or mathematical intent that they specify and the actual result of the implementation? So the standard says that any implementation that produces results that are close enough to the usual algorithms presented in a standard book on matrix computations is acceptable. Okay, so let's suppose we have an implementation and we want to know whether or not it satisfies this informal specification regarding error or accuracy that's given in the BLAS standard. Okay, so let's go to a textbook. They say we can go to a textbook, and we should be able to decide like whether or not the error that's produced by our implementation is acceptable. And we can maybe think of it as being acceptable if it's like in the same limit as is specified in a textbook here. So this is a theorem from a standard numerical analysis textbook. It's the error for matrix-matrix multiplication. And here we see they have their like inverted hat. That's our floating point matrix. And they're saying, okay, well, the error, so the difference between our computed result and the exact result, that's this AB, is going to be something like delta C, which is a matrix, where delta C is bounded by the true matrix multiplication, so the ideal result, and some constant gamma k. All right, so, well, we need to know what is gamma k. We'll go back in the book and we'll find the definition. Gamma k is defined as, for all n here is the inner dimension of the matrix, the matrices. For all n, and so long as n times machine epsilon, where machine epsilon is the relative rounding error for a single floating point operation, and it's dependent on the precision of your format. So like it will change for double versus single precision. So long as the dimension of our matrix times machine epsilon is strictly less than 1, then we can define gamma sub n as this formula. All right, well, we have to look at this assumption carefully. So it turns out that textbook error bounds don't apply for low precision. So in this plot here, I have matrix size on the horizontal axis, and this matrix size times the machine epsilon for varying formats. So we saw floating point like a 16-bit, 32-bit, and 64-bit formats, as well as this B-float. So that's like Google's tensor processing unit version of the IEEE 16-bit format. So these are all plotted, right? And we see that like for pretty small matrix sizes, so this is 100, so where the matrix size is 100 and this is 1,000, like for pretty small matrix sizes, we have n times machine epsilon is 1. So that means, in particular, that accuracy in low precision regimes is pretty much unspecified by the BLAS standard. All right? So that brings into question, right, this statement that providers of the BLAS interface can aggressively optimize while clients rely on a stable interface. So in particular, our providers might want to aggressively optimize by using lower precision formats. Okay, and well, some clients really do need, they have error requirements, right? So I might have a client who requires error strictly less than some bound. And this isn't just like an academic exercise, so there are plenty of examples in the literature. So for instance, in weather forecasting, low precision linear algebra produces completely incorrect results due to insufficient accuracy. So if we want to use something like lower precision IEEE FP16, it won't be sufficient in this domain. All right, so here we have an example of where a client requires an error bound for their results to be correct. And the BLAS interface doesn't really provide that, right? So ideally, providers would ensure the accuracy or provide some guarantee, published guarantees about the accuracy of their BLAS implementations, but you won't be surprised that they don't. Okay. So this is where I think formal specifications can help align BLAS implementations with their mathematical intent. And I have some evidence to support the claim that they actually can. All right, so in particular, we developed LA Proof, which is a library of formal proofs of accuracy and correctness for linear algebra programs that connects functional specifications of linear algebra implementations to accuracy guarantees, and we use RocQ. Okay, so what does LA Proof define? Well, LA Proof defines floating point functional models and accuracy theorems for BLAS operations. So we have vector operations, the BLAS 1 level operations. We have matrix vector operations, and we also have matrix operations. So this is following that BLAS level 1, BLAS level 2, BLAS level 3 set of ops. And functional models, okay, so what is a functional model of a BLAS implementation? Well, it is a functional program in RocQ. So here I have a definition of a dot product, and we use the mathematical components library to write our functional specs. So here, x and y are our vectors, a row vector and a column vector, and we're computing the dot product between those. And maybe it is a little small on the screen, but on line 5, we take a floating point sum. On line 6, all our multiplications in the dot product are binary multiplications over floating point values. So this is a floating point functional model. It takes floating point vectors, and it computes a floating point result. Okay, so we can connect our functional specs to accuracy guarantees by relating a floating point functional model to a real valued functional model. So in particular, these are like the same format, right? In many ways. Here on the left-hand side, we have a floating point dot product, so our floating point functional model. And then on the right side, we're everywhere where we had f type t, everywhere we have a floating point type, our real valued model of that is just instead defined over the reals. All right, And so there are really two kinds of accuracy theorems that we prove. So forward error, which is really very intuitive in the sense that you want to compute the distance between the results. Right, so I have my real dot product over an input, my floating point dot product over an input, and then the forward error just tells you the difference between the floating point and real valued or infinitely precise result. But in numerical analysis, we're also concerned with what's called backward error, which essentially measures the error in the input space rather than the output space. And this is very useful in a lot of physical science domains where the data that you're computing on itself has some kind of error due to measurement, for example, and you want to be able to compare the error due to measurement to the floating point error that's accumulated over a computation. All right, so once we have our real functional models and our accuracy proof, we can connect our functional specification, which is our floating point functional model, directly to implementations by proving a refinement proof of a C implementation of our floating point functional models using something like VST and RocQ. And so we do this in LA proof. We provide an example of connecting our accuracy guarantee directly to a C program that's a sparse matrix vector multiplication. All right, so what are the criteria for useful accuracy theorems? Suppose you wanted to prove an accuracy theorem for a linear algebra operation. Well, there are four that we've kind of determined are specifically interesting or needed criteria for useful accuracy theorems. The first one is soundness. That's not surprising. Secondary to that is that the accuracy theorem should provide a tight error bound. Third is they should be broadly applicable. And finally, compositional. All right. So useful accuracy theorems are sound. What does this mean? In an intuitive way, I have a plot here where errors are these, so like empirically observed errors for a matrix-matrix multiplication. Errors that are observed are solid lines. And error bounds, that's like a theoretical bound that we've proven, is going to be the dashed line. What does soundness mean? Okay, it means that your error bound should always be an upper bound to the observed error. Okay, so how do we actually guarantee sound bounds? Well, first we use a faithful formalization of the IEEE 754 semantics for floating point arithmetic in RocQ. So this is provided by the Flock library, a floats for coq library. And what are the semantics of floating point arithmetic, or specifically floating point operations that are provided by the IEEE standard? Well, it says that every operation shall be performed as if it first produced an intermediate result correct to infinite precision. So that's the usual infinitely precise computation that we would think about for a single operation, and with unbounded range, and then rounded that result according to one of the attributes in this clause. And so the IEEE standard defines essentially 4 rounding modes where there are some variance on this round towards nearest. And here I have an example of round towards nearest. So if this is my real number, I'm going to round to the closest float. But it also has some other rounding modes, 3 others in particular: round towards 0, round towards positive, and round towards negative. So these are the rounding modes that are described for floating point operations by the standard, and they are integrated into the Flock library. Okay, so what does this mean for a specific operation? So what it means is that in RocQ, we can prove accuracy theorems for each basic floating point operation. So here I have a accuracy of a floating point multiplication. What it's doing is it's taking 2 floating point numbers, and it's saying as long as the result of the multiplication is finite, so that means it doesn't overflow, it can fit inside of the format that we're rounding to, there exist 2 error terms, and we can exactly represent a floating point multiplication as the real multiplication scaled by some error plus some additional error value, and we have bounds on those error values. And here, in LA proof in particular, we define the binary or floating point multiplication as using round towards nearest. All right, so how do we actually guarantee sound bounds in practice? So of course, yes, we use this faithful formalization of the IEEE semantics. We also connect bounds to real C programs using VST. But if you actually wanted to guarantee that your bounds are always upper bounds for every possible execution of a program, you need to use a proved correct compiler that also respects the IEEE semantics. And then you also need to execute on IEEE 754 compliant hardware. All right, so that was soundness. The second criteria is that useful accuracy theorems are tight, so that it means they're not overly pessimistic. So if we look at this plot again, where our solid lines are observed error and our dashed lines are error bounds, then tightness means that smaller is better. We really should ideally have some very small delta of difference between our observed bounds and our sound error bounds. Because, for instance, I could just say an error bound is infinity, and this is not useful at all. Third, useful accuracy theorems are broadly applicable. They're not overly restrictive. So an example of an overly restrictive accuracy theorem that we saw previously was one in which we had this assumption that the size of the matrix times the machine epsilon, so the format that we're computing in, is strictly less than 1. And this was overly restrictive in the sense that regarding the assumption of it being strictly less than 1. And finally, useful accuracy theorems are compositional. So for example, we had our dot product functional model, and if we define a matrix multiply in RocQ, it's going to use probably that dot product. And so here on line 6, we're using the dot product inside our matrix multiply, and so we should very easily be able to use any accuracy theorem about the dot product, so relating this floating point functional model to its real functional model. We should be able to use that accuracy theorem in a very simple compositional way inside of the accuracy theorem for a matrix multiplication. So now this begs the question, does LA proof provide useful accuracy theorems in practice? So we have a case study where we used LA proof to prove the accuracy and convergence of a linear solver, so a solver for a linear system of equations, where it's actually called the Jacobi method. And the problem is, right, something we saw at the beginning of the talk. We're given a coefficient matrix, we're given a constant vector, and we need to find the solution vector. And what the Jacobi method does is it takes the diagonal elements of the matrix A that we're given, and it iteratively updates the solution vector using matrix vector multiplications. So at every step, we use a matrix vector multiplication. And so this is a case study where I will argue that LA proof does provide useful and accuracy theorems in practice. So this is a plot provided from a PhD thesis that my colleague wrote, actually, on proving the accuracy and correctness of the Jacobi method. Okay, and so blue line down here is the computed error over iterations, so where iteration is k. And then up top we have our theoretical error bound, so the error bound that he was actually able to prove using LA proof for each of these matrix vector multiplies. Okay, and that clearly this is sound, right? Our theoretical error bound is a sound upper bound to the observed error. It's fairly tight. It's actually nicely surprising. It's only a factor of 2 larger. And it's compositional in the sense that we were actually able to use LA proof, right? This is multiple iterations where we have to use our matrix vector multiplication accuracy theorem. So it's compositional in the sense that we were able to use all of the accuracy theorems for the basic linear algebra operations that are provided by LA proof to prove a tight and sound accuracy bound for this iterative method. All right, so that's 3 of the 4 criteria. But are they broadly applicable? This is only one case study, and I argue in some sense they are, specifically because, now I don't actually expect you to read this at all, but this is our theorem on the matrix multiplication error, so the accuracy of the matrix multiplication in RocQ. And if you wanted to, you could go and look through it. But what you will find is that we don't actually have this assumption from a textbook error bound. We didn't need to make use of it. And actually, at a high level, it was very nice because what happens is that numerical analysts, it's kind of a pain to take care of all of the higher order error terms that appear in a very large error analysis of something like a matrix multiply. And what they do is they use classical identities to try and account or capture higher order error terms in a really easy way to do on paper. But when we use a proof assistant, we can kind of do all of that accounting without having to worry about things being incorrect. So we didn't have to actually make this assumption at all in our proof. So in some sense, LA proof error bounds are not overly restrictive in the same way that they would be from a textbook proof. But they might be over-restrictive in a different way. So applications, that means application scientists, people, clients of the basic linear algebra subprograms, they're embracing stochastic rounding. So for example, in climate modeling is a place where people really want to use stochastic rounding. This is a different type of rounding from the 4 formats that the IEEE standard specifies. And what these people say in this study is that they looked at the efficacy of low precision arithmetic for climate simulations. And by testing models using both round to nearest, so that's an IEEE standard rounding mode, and stochastic rounding, we found that stochastic rounding can mitigate rounding errors across a range of applications. And thus, our results also provide some evidence that stochastic rounding could be relevant to next generation climate models. So many application scientists outside of climate modeling as well are really finding that stochastic rounding has a lot of benefits, especially when you're using a low precision in your computations, and they want to use low precision because it makes things faster. Hardware is also embracing stochastic rounding. So there are a few examples, like the GraphCore IPU supports both IEEE half precision and stochastic rounding in hardware. AWS's Trainium also supports IEEE half precision, not just for storage, but also for computations, and uses stochastic rounding or implements stochastic rounding in hardware. But LA proof does not support stochastic rounding. So in some sense, are our accuracy theorems really applicable to like next generation computing? Are they really providing the kinds of accuracy theorems that application scientists will want? And the answer is no. And again, before we had this lemma about the accuracy of a floating point multiplication, and I said like we define it assuming round to nearest. Okay. So this is where we find the need to future-proof accuracy guarantees. So I think that stochastic rounding provides an opportunity to us as people who are interested in writing formal specifications for software, but also for hardware. So in particular, it provides the opportunity for us to isolate rounding mode assumptions. So some properties that are trivial and round to near, so a lot of properties that are like trivial and numerical accuracy theorems that use round to nearest don't hold under stochastic rounding. And other properties of round to nearest do continue to hold under stochastic rounding. And I think that if we can isolate these properties systematically, then that will help us identify like which proofs in numerical analysis, and specifically which proofs in the accuracy of basic linear algebra operations are robust to new hardware rounding modes. And secondary, I think it presents an opportunity for us to extract reusable proof patterns. And I wish I could make this a little bit larger for you. But this is a theorem of matrix-matrix product accuracy where the authors are using stochastic rounding to prove a rounding error bound for matrix-matrix multiply. And the result that they have has the same overall structure, and the proof has a very similar structure to what you would find for a non-stochastic rounding, so for any of the IEEE standard rounding modes. And so the idea is that we'd really like to be able to extract like the proof patterns that a numerical analyst would use for any kind of proof about accuracy for linear algebra operations by looking at the similarities between linear algebra proofs of accuracy that use standard rounding modes and linear algebra proofs of accuracy that use these non-standard rounding modes. And I think that we can use stochastic rounding as an opportunity to do that. I think this is also important, extracting reusable proof patterns, because ideally we have robust, insightful, and easy to read proofs because these will help strengthen the argument for formal specifications in basic linear algebra in the numerical analysis community. And just anecdotally, I did a PhD with a numerical analyst where I was co-advised by someone who works in formal methods. And I would really write these like long proofs in RocQ, right, of numerical accuracy, and I would bring them to my advisor, and he did not want to look at them, which is not surprising, right? He's a numerical analyst. He wants to know, like, what is the high-level, insightful thing about this proof? And so it is very important for us when we're trying to interface with people from other domains to try and kind of isolate the most insightful parts of our proofs. And I think that if we can extract the reusable proof patterns from our LA proof proofs, then this will very much help with making the argument for providing formal specifications in the basic linear algebra operations. Now, similar opportunities arise for non-IEEE arithmetic formats. So there are many kind of new next generation formats, arithmetic formats that people are trying to use in different areas of computing. Probably one of the oldest and most popular ones that people are discussing these days are Gustafson's posits. And there's been sort of a long history of argumentation about whether posits are actually a reasonable format to use for computing. And it's been sort of very heated in the numerical analysis community whether these are ever going to really be appropriate for computing at all. Partially because in order to use posits, numerical analysis will have to essentially be completely rebuilt. And while this is, probably a bad thing if you want to have reliable computing, I think that for us, it's a potentially useful case study for identifying pain points in formalizing non-IEEE formats. And again, so I said, like in stochastic rounding, one of the reasons I think that we should really be considering formalizing this and trying to like future-proof accuracy guarantees with respect to it is because both, it's application designers as well as hardware designers are requiring it or wanting to use it. They're embracing it. And just in the last year, so a couple of years, in 2024 was the first multi-core RISC-V processor with a hardware implementation of posits. So whether or not people in the numerical analysis community sort of agree with the use of non-IEEE formats as a reasonable thing, I think it is probably something that will continue to be sort of emphasized by both the hardware and application communities. And that if we can, as formal methods folks, start to consider like what are the real pain points in formalizing these non-IEEE formats and what are the pain points of incorporating these formalizations into proofs, then we can kind of maybe provide useful ideas to the numerical analysis community. All right, so my argument really is that the RocQ community can help future-proof numerical accuracy by formulating formal specs for linear algebra operations, so for the basic linear algebra operations. I made the argument that informal BLAS specifications have enabled decades of success in numerical linear algebra. They really have been consequential in the same way that new hardware improvements and new algorithmic improvements have been to the success of numerical linear algebra. And I think because of the role that informal specifications have played in that area, I think that we as people who are concerned with formalizing specs, that we have really an opportunity to try and interface with people who are designers and clients of BLAS. So accuracy is also left entirely unspecified by the BLAS standard, right? For low precisions as well as for new rounding modes and formats. I made this argument. And I think that as far as future proofing, what we can do is formalize accuracy theorems that include low precisions, as well as new rounding modes like stochastic rounding and potentially non-IEEE formats. And formal specifications, I make the argument, can restore accuracy guarantees to BLAS implementations. And we have an example of that in LA proof, which demonstrates that BLAS level accuracy guarantees can indeed be mechanized and applied to real world programs. And my hope is that LA proof can sort of serve as a template for extending formal specifications in numerical linear algebra, again, to include things like low precisions, which we can, our accuracy theorems do hold in LA proof for things like low precisions, but extending them to include new rounding modes and formats, I think will be very insightful for the numerical linear algebra community at large, but also very useful exercises for people who are interested in formalizing numerical accuracy in theorem provers like RocQ. And so with that, I would like to conclude and welcome any questions.
We have time for questions. If anyone, feel free to raise your hand and we'll send a microphone your way. Okay, I can get us. Oh, okay. Oh, you'll take the next one. Okay, so with these stochastic rounding things, right? I assume it's sort of randomized, right? So yes. Here, to get a tight bound, wouldn't you want to have some sort of, I don't want to say here, sort of amortized or average error analysis, or do you still want like a tight upper bound?
So the stochastic rounding actually provides a tighter upper bound in general, and that's why a lot of people or numerical analysts, part of the reason that numerical analysts have been interested in it historically. Well, they've been interested in probabilistic error bounds historically, but those aren't necessarily sound. Mm-hmm. But if you use stochastic rounding and then you perform a probabilistic error analysis, then you can, the sound bounds work. And really what's happening is when you're using something like round to nearest, the errors are often correlated. But when you use stochastic rounding, in the mean, right, your errors might actually cancel, and they do in practice often cancel out.
And that's not a probabilistic argument that they cancel out?
It is a probabilistic argument that they cancel out, yes.
And would that have to be reflected in the specifications?
That would have to be reflected in the specifications, that's right.
Got
yep.
It.
So there is, it's not so simple probably to actually formalize stochastic rounding inside of the proof assistant. We will actually have to probably include different libraries for probabilistic reasoning and so, in order to support stochastic rounding.
Makes sense, thanks.
Yeah.
Can you? Sorry. So this is really cool. What can you say? So do a lot of people use C or C++, or what is the common things that people actually code this stuff in? And then I imagine a lot of them, Fortran. Okay.
Yeah, Fortran. No, but so earlier on, it was very small on the screen. But when I said, like, what does the BLAS standard define, and it has a standard interface, it's a Fortran API and a C API, and there are C implementations of BLAS. So people use C, they use Fortran. Now some of these are being ported to C++, but historically it's been Fortran and then C. So the idea that we can formally verify these programs is not completely absurd, right, if most of them are written in C.
Yeah, so coming back to the stochastic rounding, which I discovered in your talk, thanks. Is it really non-deterministic in that if you run the same program twice, you can get different roundings? Or is it kind of a hidden function? The rounding is an unspecified function of the values of the arguments, some kind of pseudo-random function, but still a function.
So theoretically, it is truly non-deterministic. So if I round a value, it will not always, the result will not always be the same. As far as the actual implementation, right, we may or may not have true non-determinism.
Okay.
Yeah.
Well, that makes a big difference for proofs like concerts, semantic preservation proofs. So that's why I was asking.
Yeah.
Thank you.
Yeah. Yes, so actually connecting, any formalization of stochastic rounding in the proof assistant to real implementations is a very open question.
For certain problems like inversion of matrix, you can use an iterative process, and you stop when some test is satisfied.
Yes.
So in that case, you don't have to propagate errors during the iteration process, because it's the stopping condition that will describe the precision. Is that the case, or?
Yeah. So if we go
in
back
my conversation with Mohit, it was the case, I believe. But,
yeah. So if you're computing the stopping condition also in finite precision, and the stopping condition is like for the method that Mohit was working on in this case. You're looking at the difference between the computed result and like some your ideal vector that you're given in the first place,
or between successive values in the vector.
You are looking between successive values, yes, and the user defines this tolerance.
So this was the context of my question. Now, could you consider having part of the computation done in one rounding mode, and the other part, like the verification, being done in another rounding mode, and how much does it impact your work?
If you're saying the computation is done in one rounding mode and then the accuracy theorem is in a different rounding mode?
Yes.
You would have to account for that in the accuracy theorem. It could be done.
It may make sense. It may not make sense.
I don't see necessarily a reason for it, as long as the rounding in the implementation is an IEEE rounding mode. Like, you can model that in the accuracy theorem itself, but not for stochastic rounding.
Yes. But you also talked about using. You said you used the rounding to nearest in most of your computation, but the very precise specialists in arithmetics, they don't stick to only rounding to nearest.
Oh, they might use something like round to odd instead, but you can include this in your specification as well. Yeah, I mean, we have not in LA proof. We assume always round to nearest. Yeah, but this is also the case for the general accuracy theorems that are given in the textbooks for basic linear algebra. So maybe, like, if you're looking at some very different computations, you might use a different rounding mode. But in the BLAS implementations, they're always using, for the most part, round to nearest. Yeah.
Okay.
With some
maybe
caveats.
we can take this offline.
With some major caveats. Okay. Thank you.